Hi there, this is Ayush from Master Mechanical Design, and today we will master a very crucial concept of GD&T, which are worst case boundaries. Inner boundary, outer boundary, virtual condition and resultant condition. These boundary conditions are not only fundamental in design, but they are also very common question in interviews. But before dive into each boundaries and their calculation, first I want to give you an idea of why these boundaries exist and why they are so important. So to help you to really grab this, let me start with some simple examples of fit and no fit. But in case if you are in a hurry, you know what to do. Jump to the specific chapters. And lastly, please excuse me for my voice today. I have a cold. So let's say we have a shaft with diameter 20 mm plus minus 1 mm, and we have a hole in a block, of course, with diameter 21.5 mm plus minus 0.2 mm. So can you tell me, will this shaft always fit in this hole, always pass through this hole? So to check the fit and no fit condition, what we do? We check the fitment clearance at worst case scenario. And what could be the worst case scenario for any fitment? You already know, when the shaft is at largest size and at the same time hole is at a smallest size, right? So the largest size of the shaft would be at its MMC, maximum material condition, would be 20 plus 1, 21 mm. And for the hole, the smallest size will be also at its MMC, would be 21.5 minus 0.2, 21.3 mm. So there will be always at least 0.3 mm clearance or positive clearance between the shaft and hole, means the shaft will always pass through. Simple enough, right? So let's make the things little interesting. Let's apply a stiffness tolerance of 0.5 mm over the shaft surface, something like this. Now, what do you think? Will the shaft pass through this hole? So yes, definitely this will, because the stiffness tolerance applied over the shaft surface doesn't make any difference, any change in worst case fitment condition. Why? Because according to GD&T rule 1, which is perfect form at MMC, means when the shaft is at MMC at 21 mm, the form of shaft must be perfect, no matter whether stiffness is controlled or not controlled over the surface. Means the stiffness tolerance, stiffness deviation of the shaft will become automatically zero when the shaft diameter is at its MMC at 21 mm. Also same for the hole, when hole will be at its MMC at a smallest size 21.3 mm, the form of hole should be perfectly cylindrical, whether stiffness is defined or not defined. So the shaft maximum size will be still 21 mm even with 0.5 mm of a stiffness tolerance. So the shaft will always pass through this hole. But what if we apply same stiffness tolerance to the size dimension of the shaft instead of applying over the surface? Will the shaft still pass through this hole? So now the situation change. When we apply a straightness or a flatness tolerance to the size dimension of a feature of size, like so, below or next to the dimension, the straightness tolerance applied to the median line, not to any surface, and the flatness tolerance applied to the median plane, not to any surface. And in these two conditions, GD&T rule 1 doesn't apply. This means even at MMC, the shaft can have defined allowable stiffness deviation. Like it may be slightly bent, something like this. Perfect form at MMC is not longer required. So the shaft at its MMC of 21 mm, the median line could be bent up to 0.5 mm, defined maximum stiffness deviation. This means the extreme outer boundary of the shaft could be 21 mm MMC of the shaft diameter plus 0.5 mm straightness deviation, 21.5 mm. So this outer boundary of the shaft is now larger than the inner boundary of the hole. So in this case, the shaft may not pass through this hole. There could be up to 0.2 mm of interference. So as you've seen that the relation between geometric tolerance and the extreme boundary of a feature of size is crucial. Even though these were very simple examples, we only defined one geometric control over the feature of size. But in real-world design, especially in complex assembly of machines, we often define multiple geometric tolerance to the single feature of size. For example, to this pin, we apply a position tolerance of 0.5 mm along with a straightness tolerance of 0.5 mm. Moreover, most of the time we define these tolerances at MMC to take the advantage of bonus tolerance. Learn more about MMC, LMC and bonus tolerance in this video. Check it out later. So what I all want to say is, as a designer, we must be able to calculate the worst case boundaries of any feature of size, considering all the geometrical variations. Also when different material conditions are applied in feature control frame to ensure the proper mating of two parts. Also, we need to calculate the worst case boundary in designing a functional gauge for a part inspection and also for engineering calculations, tolerance stack-up analysis. So this video is a complete detailed analysis of worst case boundaries. But worst case boundary is a very general term. Every extreme boundary of a feature of size refers as worst case boundary. So to make things clear, we break down worst case boundary in four specific terms: inner boundary, outer boundary, virtual condition and resultant condition for both internal and external feature of size. So this gives us total 8 boundaries: 4 boundary condition for external feature of size and 4 boundary condition for internal feature of size. However, virtual condition and resultant conditions are applied at MMC and LMC. So we refer them as virtual condition at MMC, virtual condition at LMC. And same for the resultant condition at MMC and LMC for both internal and external feature of size. So in total, this brings us to 12 worst case boundaries. It seems like a lot at first, but not actually. Virtual condition and resultant condition are actually a variation of inner and outer boundary with addition of material condition modifier. As we go through the examples, you will see that how straightforward this becomes. There's nothing complicated. So let's start with inner and outer boundaries. So let's start very lightly. Let's take a pin, an external feature of size with diameter 20 plus minus 1 mm. So if there is no geometric tolerance is applied, just size tolerance are there, then the outer boundary will be its MMC size, which would be 21 mm in this case. And the inner boundary, the smallest boundary, would be LMC size, which would be 19 mm, very simple. Now let's add a geometric tolerance. Let's suppose this same pin is on a block like a locating pin, a dowel pin, with defined position tolerance of 0.5 mm relative to datum A, B and C. So for outer boundary, first up, the largest diameter of pin would be considered, means MMC of the pin, which is 21 mm. And here I have indicated MMC surface with blue line at nominal position, at 0 position tolerance relative to datum A, B and C. Now, as the position tolerance is 0.5 mm with diameter symbol, this means the position of this pin's center line can move anywhere within 0.5 mm diameter from its nominal position. Means this pin center line can shift 0.25 half of the diameter 0.5 on the left side and 0.25 on the right side from its nominal position, right? So I have indicated this shifted pin surface with red lines. So this shifted red lines pin surface is shifted by 0.25 mm from the pin surface at nominal position from the blue line surface. And this shifting of 0.25 mm of the pin surface would be from all around. So the outer boundary would be 21 mm MMC of this pin plus 0.5 mm maximum position deviation, 0.25 from left, 0.25 from right, 0.5. So this will make the outer boundary 21.5 mm. Very simple geometry. Now let's add one more geometric tolerance to the pin to make you more clear about outer boundary calculation. So let's apply a straightness tolerance to the pin surface. So you already know the answer. The outer boundary stay the same, 21.5 mm. This is because according to GD&T rule 1, the perfect form at MMC, no form deviation is allowed when the feature of size is at MMC, and where we already considered MMC size of the pin 21 mm, as we seen in earlier example. So you can keep this as a note in your mind, that applying a geometric tolerance to the feature, to the surface means feature, geometric tolerance doesn't affect the outer or inner boundary of a feature of size. However, if the straightness is applied to the size dimension of the feature of size, then GD&T rule 1 overridden. Means perfect form at MMC is not longer required. Means even at MMC at 21 mm, the pin can bend up to 0.5 mm, as we shown in earlier example. So in this case, outer boundary will be 21 mm MMC of the pin plus 0.5 mm position deviation plus 0.5 straightness deviation, making the outer boundary 22 mm in this case. What it actually means is, in this worst case scenario, this pin size can be at MMC at 21 mm, and at the same time this pin can have maximum offset position from nominal position by 0.5 mm in any direction, and at the same time this pin can be also bent by maximum allowable straightness deviation 0.5 mm. And of course, there can be also other geometrical deviations like perpendicularity deviation. But in this video, I'm only explaining with the position tolerance and straightness tolerance to make it simple. So to summarize, the outer boundary of an external feature of size is a worst case boundary generated by the largest feature of size, which is MMC, plus effects of all geometrical tolerance like position tolerance, straightness tolerance, or any other geometrical tolerance. To be mathematical, the outer boundary OB of an external feature of size equal to MMC plus applied geometrical tolerance. I hope this is so much clear to you. Now, what about the inner boundary of an external feature of size? So if there is no geometric tolerance is applied over the external feature of size, the inner boundary would be its LMC size. So in this case, the inner boundary of the pin would be 19 mm. Now with the position tolerance 0.5 mm. So for inner boundary, first off, LMC of the pin would be considered, which is 19 mm, and here I'm indicating LMC surface with blue line at their nominal position with respect to datum A, B and C, and as the allowable position deviation is 0.5 mm, means this pin center line can shift 0.25 on the left side, 0.25 on the right side from its nominal position, right? And I have indicated this shifted line with the red lines. So this red pin circles is shifted inward also by 0.25 mm from the left surface at nominal size And this shifting of 0.25 of surface would be from all around. So the inner boundary diameter would be 19 mm, LMC of the diameter minus 0.5 mm, 0.25 from the left, 0.25 from right, 0.5, making the inner boundary 18.5 mm in this case. If additional tolerance like a strengthness tolerance is applied, let's say 0.5 mm, then the inner boundary will be reduced further by 0.5 mm, resulting in 18 mm. So we can say the inner boundary of an external feature of size is a worst case boundary generated by the smallest feature of size, LMC, minus effects of applicable geometrical tolerance. Formula: inner boundary IB of an external feature of size equal to LMC minus applicable geometrical tolerance. Now let's understand the inner and outer boundary of an internal feature of size. So let's say we have a hole in a block, an internal feature of size of diameter 20 mm plus minus 1 mm without any geometrical tolerance. So inner boundary of this hole would be the smallest size of the hole, means its MMC size, which would be 19 mm in this case. And the outer boundary of this hole would be at its largest size, means at LMC size, the maximum space a hole can take place, can occupy, which would be 21 mm in this case. If you are thinking I'm making mistake, the smallest size of the hole should be LMC, not MMC. So no, I'm not making any mistake here. For a hole which is an internal feature of size, the smallest size occurs at its MMC and the largest size occurs at its LMC. It's just opposite to the external feature of size like a pin or shaft. More about that in this video. Check this out later. Now, if we define a position tolerance to the hole, let's say 0.5 mm, with respect to datum A, B, and C, the inner boundary of this hole would be MMC of the hole 19 mm minus position tolerance 0.5 mm, say 18.5 mm. And the outer boundary of the hole would be LMC of the hole 21 mm plus position tolerance 0.5 mm, say 21.5 mm. Now, here is a question you might be asking yourself. For mating of two parts, let's say for a hole and shaft, we ensure the smallest boundary, the inner boundary of the hole, and the largest boundary, the outer boundary of the shaft. And fitment depends on the clearance or interference between the both worst case boundaries. So for fitment, only these boundaries are important: the inner boundary of the hole and outer boundary of the shaft. So why do we calculate rest of the boundaries? The outer boundary of the hole and inner boundary of the shaft. What is their purpose? Well, so the first obvious purpose is doing the tolerance stacking calculation. But the second important purpose of outer boundary of the hole is to ensure the wall thickness. The outer boundary helps us to figure out how much material is left in worst case scenario to make sure that the wall thickness isn't too much thin and should not be zero wall thickness problem. So this was all about inner and outer boundary of a feature of size. Now let's understand the virtual condition and resultant condition. So first off, the virtual condition and resultant condition boundaries can be only defined when the geometrical tolerance applied to the feature of size is defined at MMC or LMC. If there is no MMC or LMC modifier in feature control frame, we cannot define virtual condition or resultant condition boundaries. Without these modifiers means at regardless of feature size, we define inner and outer boundary, not virtual condition and resultant condition. So if someone asks you maybe in interviews that what would be the virtual condition and resultant condition for a given feature of size, then the first thing you should do is check the geometric tolerance modifier. If there is no MMC or LMC modifier in feature control frame, or if there is no geometric tolerance applied at all, we cannot define virtual condition or resultant condition boundaries. In that case, we stick to the inner and outer worst case boundaries. If there is an MMC modifier, then we can define virtual condition and resultant condition at MMC. If there is an LMC modifier, then we define them at LMC. In this video, I am only going to explain virtual condition and resultant condition at MMC because that's what we mostly use. Defining virtual condition and resultant condition boundaries at LMC works in same way but in just reverse. So let's start with the definition and then we will break it all down. So the virtual condition at MMC of an external feature of size is a worst case boundary generated by the collective effect of largest feature size MMC plus the applicable geometric tolerance. For example, this pin, the diameter 21 plus minus 1 mm with position tolerance 0.5 mm at MMC with respect to datum A, B and C, the virtual condition would be MMC of the feature size 21 mm plus applicable geometrical tolerance at MMC 0.5 mm. So the virtual conditions becomes 21.5 mm. Now you might be wondering, this seems the same as the outer boundary of an external feature of size. So what's the difference? So the main difference is that virtual condition boundary is a fixed worst case boundary, while outer boundary is a variable boundary. Confusing, isn't it? So let's understand this practically. So in this example, if the pin size is 21 mm at MMC size, the position tolerance is 0.5 mm at MMC. So the extreme outer boundary would be 21 mm plus 0.5 mm, 21.5 mm. Now let's say if the pin size is produced at 20 mm, 1 mm less than the MMC size. So since the position tolerance is defined at MMC with MMC modifier, means the bonus tolerance will be applied here. The bonus tolerance equal to MMC size minus actual size, means bonus tolerance equal to 21 minus 20, 1 mm, meaning the allowable position deviation increased to 1.5 mm, 0.5 mm plus bonus tolerance 1 mm. So the extreme boundary would be 20 mm plus 1.5 mm, 21.5 mm. It remains the same. Even if pin is produced at 19 mm, 2 mm less than MMC, so the bonus tolerance would be 21 minus 19, 2 mm. So the position tolerance will become 2.5 mm. So the extreme boundary will still remains 19 plus 2.5, 21.5 mm, right? I hope this is so much clear to you. For bonus tolerance and MMC modifier, you can watch this video later. However, in case of outer boundary with no material condition modifier, the situation is different. At MMC 21 mm, the outer boundary would be 21 plus 0.5, 21.5. But if the pin is, let's say, produced at 20 mm, and since there's no modifier, no MMC or LMC is defined over the position tolerance, means there is no bonus tolerance. It's regardless of feature size. So the position tolerance will remain same 0.5 mm regardless of feature size. So the outer boundary would be 20 plus 0.5, 20.5 mm. At 19 mm, the outer boundary would be 19.5 mm. This means the outer boundary is a variable worst case boundary, while the virtual condition is fixed boundary. So the both virtual condition and outer boundary establish boundaries to ensure the assembly, but virtual condition allow bonus tolerance to keep adjusting the same boundary, fixed boundary, and most importantly establish the size for functional gauge. the acceptance boundary for inspection, while outer boundary or inner boundary cannot consider as acceptance boundary for inspection, because outer and inner boundary cannot ensure the size deviation and the geometric tolerance together. For example, here the outer boundary of the pin is 21.5 mm. MMC of the pin 21 mm plus a straightness tolerance 0.5 mm. Now let's say if the pin is produced at 20 mm with a straightness deviation 1.5 mm. So the outer boundary will remain same, 20 plus 1.5, 21.5 mm. Doesn't crossing the outer boundary, but the pin is rejected. The straightness tolerance is out of limit of 0 to 0.5 mm. So we cannot trust the outer or inner boundary as an acceptance boundary for inspection. Whereas if this straightness tolerance is defined at MMC, then the virtual condition would be the same, MMC 21 mm plus 0.5 mm. And now let's say if the pin is produced at 20 mm with a straightness deviation 1.5 mm, then it's completely fine, because as much the size is reduced, the bonus tolerance increase. The virtual condition boundary remains the same. In other words, if the feature of size is under the size limit, in this case 19 to 21 mm, and passing through the virtual condition boundaries, then the part will be always acceptable. You don't need to check the geometrical variation separately, because the bonus tolerance will be there. It's acceptable. And this is why MMC modifier with geometric tolerance reduce the inspection cost, because I just need to pass through the inspection gauge. Whereas the geometric tolerance without any modifier is difficult to inspect. You will need CMM, but we cannot always define MMC modifier with every geometric tolerance. It's all depend on the application. More about that in this video. Now, what about the resultant condition? So, resultant condition is opposite of virtual condition. Like as the virtual condition is the outer boundary at MMC, so the resultant condition is inner boundary at MMC. So resultant condition at MMC of an external feature of size is a fixed size worst case boundary generated by the collective effect of a smallest feature size LMC minus applicable geometric tolerance. So in this example, the resultant condition would be 19 mm LMC of the pin minus applicable geometric tolerance 0.5 mm, 18.5 mm. And now let's understand these both conditions for internal feature of size. So the virtual condition at MMC for an internal feature of size is a worst case boundary generated by the collective effect of a smallest feature size MMC minus applicable geometric tolerance. So this is the same as the inner boundary of an internal feature of size, but with MMC modifier. So in this example, as this whole size is 20 plus minus 1 mm is defined at position tolerance 0.5 mm at MMC. So there is an MMC modifier. So we define virtual condition instead of inner boundary. So the virtual condition at MMC of this hole would be MMC of hole 19 mm minus applicable geometric tolerance, position tolerance 0.5 mm, 18.5 mm. And this is a fixed boundary, means if the hole size increases, means if the hole size go towards LMC 21 mm, by the same amount of increment in size, the bonus tolerance will add up in position tolerance. So when the hole is at 20 mm, 2 mm more than MMC, so the bonus tolerance would be 2 mm. So the position tolerance would become 0.5 plus 2, 2.5 mm, and the virtual condition boundary would be 20 minus 2.5, 18.5 mm. The boundaries remains constant. And the resultant condition at MMC of an internal feature of size is just opposite to the virtual condition at MMC of an internal feature of size. Means the resultant condition at MMC of an internal feature of size is a fixed size worst case boundary generated by the collective effect of the largest feature size LMC plus applicable geometric tolerance. So in this example, the resultant condition would be 21 mm LMC of the whole plus the applicable geometrical tolerance 0.5 mm, 21.5 mm. So this was all about the worst case boundaries: inner boundary, outer boundary, virtual condition, and resultant condition. So just for a quick recap, inner boundary and outer boundary are very straightforward as their name suggests, the extreme boundary of an internal feature of size and external feature of size. We define inner and outer boundary when geometric tolerance is defined at regardless of feature size, means at no MMC or LMC modifier. But when the geometric tolerance is defined at MMC or LMC, then we define virtual condition and resultant condition. And just to keep in mind, virtual condition defines the worst case boundary of an assembly condition. Means virtual condition at MMC of an external feature of size is the extreme outer boundary at MMC. And the virtual condition at MMC of an internal feature of size is the smallest inner boundary at MMC. And the resultant condition is just opposite to the virtual condition. We do the calculation of resultant condition boundaries to make sure the wall thickness in worst case scenario. And for your practice, I'm leaving this PDF in drawings where you can calculate the worst case boundaries. You can download this PDF from video description and you can let me know the answers in comment. And thank you so much for the watching.